like three or 4 months ago. Because I wrote an email to one of the main developers of the Python project that is a very good project for storing scientific data, that's called tables. And I wrote an email to him and I said, I'm not going to improve this code anymore because now I'm moving everything to Python. And I'm to Go, sorry. And it was the first time I heard about Go. I said, okay, this guy is moving everything to Go. It is something I have to learn and have to do. So I started with the tour of Go. I started reading tutorials and blog posts and things like that. And I said, wow, this is something good. What I like of Go is that it's a very simple language. It's very easy to learn. In just few weeks, you can learn pretty much everything of the language. It has a very limited collection of libraries, but in a good sense that they have not a lot. There's not a lot to learn, but the ones that they have, they are very good. So I used it operationally in this pipeline that we are doing. And what I did is I did a RESTful API for the interface with the pipeline. And we created this web application using Go with very few, with just a few lines of code. Like you can realize how good it is. And when I started telling my colleagues and say, oh, you have to use Go, Go is very good, look at this code. And after I realized about the group, the Gophers group that you have set up and has been running in Sydney once a month since, for how long?
It's been coming in 7 months.
Like 2 years. And I wrote an email to these guys asking, oh, I want to do something similar in Canberra. To have like a meeting or a meetup group in Canberra for having people talking about Go. And I say, okay, let's do it. Just find a venue and send an invitation and see how it goes. And yeah, I think that's it. We're here now. So I'm not going to talk longer. I just give it to you. And they're going to listen. Like Dave is going to present a short introduction to the language compared to other languages, what are the differences, what you is that right? Yeah. Okay. And after Andrew will talk more about the ecosystem tools and things and where the community is now in the eyes of the cool projects happening in Go. So that's it. Thanks for coming.
Thank you everyone for coming. There's 19, we're 19 on the I think there are 19 people. That is exceptional achievement. When we host a meetup in Sydney, maybe half of the team come. So really thank you very much for coming out. So yeah, thank you to Ella for putting this on, especially for finding the venue. Like, as an organizer myself, it's the hardest bit. You get songs and everything, or organize the time, so that's a huge thing. Also, I don't know if there's anyone here representing Sorry, but thank you for the space. Very much appreciated. And yeah, thanks everyone for coming tonight. My name is David. I work for Chronicle in Sydney. I have been involved in Go since 2010. I think I kind of got involved early. And I'm the co-organizer of the City Go Users Group along with Andrew. I had the opportunity to travel and speak in a whole bunch of places about Go. That's one of the things I like about it. That I can always go to a new city and talk to people about the language that I enjoy in my life. So the first talk of the first meetup is always going to be a little bit different. This is what I was thinking of doing. Good thing is this is a small group, so within reason, just if I say something's confusing or doesn't make sense, or you want to make it, then raise your hand, have some questions. The basic idea is to talk a little bit about the history of Go, like why another language, an overview of the language, hopefully to point out where similarities and differences between other languages that maybe you use in your jobs. A little bit of an overview of the tools. Like a language is as hard a specification written on a bit of paper. The tools are actually when the road meets the road, and probably some questions. Before I come on to the next slide, I just want to get a kind of feeling of what is the, so who has used Go already? Just for a bit, yeah. So the rest of you are just kind of interested, or and of those, what is your Python, what are some of the other languages? C? Yeah. Any? Okay, so I'll try and at least try to point out commonalities and differences between that. I know a lot about what I'm saying. So why not another language? As Andrew was talking beforehand, Andrew said Go started by Rob Pike, Robert Grusner, and Thompson, somewhere in late 2007. Russ Cox and Ian Lansdale joined a little bit later, and they're really who we think of as the core of the Go team, although it's now much bigger than that. I'll talk about. There's a story that Go was designed already for a C++ program to compile. Maybe that's true. Maybe it's not. More importantly, Go is a response to the environment that Robert and Ken were working inside Google. The tools that they have, the languages, mainly C, Java, and Python. And throughout this talk, the slides will be online again. There are lots of links which go into, you don't need to write any of this down, which go into a lot more detail. The public announcement was 10th of November 2009. That link over there is the link to the video. You can watch the first announcement. And I put this screenshot here because this would really, if you want to capture the ideas of this language, it was perhaps these 5 things. Efficiency of a statically compiled language, easy programming of dynamic language. Safety, both in terms of type safety for a statically typed language, and memory safety. Possibly the way that we don't know that in C and C++. Good support for currency and communication, so networking. Efficient latency-free garbage collection. I have to come back to that. And high-speed compilation. We look at the 5 dogs that came from that tool. Pretty much over the last 4, coming on 5 years, I don't think the focus has really changed. That's still, those original goals for the language are still hold true. It's an open source project. All the commits, all the code review, all the design, it's all done on a public mailing list. Some people are paid to work on Go for their jobs, some people are paid to work on it for their spare time, but it's all done in public. Really, the only qualification is if you've got time to spare on it. So, in the 2 and a bit years between when Go was publicly announced and March 2012, which when we had the 1.0 release, there was a lot of rapid iteration. Many things in the language changed. But around the start of 2012, the decision was made that an important point of focusing would be to say that this language, which we had 5 or 6 releases, it was very much a moving target. I know people are following Rust at the moment, but Rust's moving target kind of thing at the moment is very much where Go was 3 and a bit years ago. So the decision was made to let's do a 1.0 release, and from that point onwards, the language effectively will not change. This is the point of stability that people can build on. That kind of decision was codified under this thing called the Go contract, which is basically all the symbols that you know aren't going to change. The language that it is today, as defined 3 years ago, is the language as it is today. With a few minor additions, but only very minor ones. And so from that point on, we've been with 3 major point releases, 4th one is in the works. After a little bit of a bumpy start, the first point release, we roughly work on a 6-month time frame, so it's about 3 months active change window and a 3-month stabilization period. We've set the ship dates up front and basically work to those rather than when it's ready. Most important, really big changes are discussed publicly first before the change window opens. It is just a free roll. And over this time, we've added new platforms, Solaris, all the BSDs, new architectures, and each of the releases brought incremental improvement, compilers, runtime, and garbage collector. So that's really the focus since the 1.0 release. And 1.0 for us means stability. And honestly, when the code that you write today, or wrote 3 years ago for Go 1.0, will continue to work into the future. And I really don't know, with the possible exception of Java, languages that can actually make that, certainly for the Python programmer. That is certainly not as true. But we assert certainly we commit. We have as part of the build that happens after every check-in. We assert that every one of the symbols is defined for releases is not changing. Leave anything, not change the contract specification on equal the method of finding that. This stability through this contract does have a downside, and that is that the bar for changing language is insurmountable. The language that we have, the stability, is good, but it is now the language that we have to learn to use. Yes,
but that is kind of a good thing. Thinking of Rob White's philosophy that less is more. And I think he commented at one point, someone from the C++ community said, "Oh, good news for C++, we're adding 26 new features." Like, did you need 26 new features? Especially when it means, oh, now your old code has to be reworked or something like that. Yeah, it's bad.
I agree. It is certainly a point of frustration for people coming into the language. They either reopen old debates or have new ideas that we just can't accept into the language. But I think, on balance, the stability, we paid a very high price for that up until now for this stability. There are little things and inconsistencies that would be globally fixed in language, but that would mean the break is not. So this next section is an overview of the language. I'm going to go through it pretty quickly and try and talk to it, probably try and contrast it with the things that are similar or different to languages that people have told me they use here. I think that's useful. So safety. Obviously, Go is a type safe. Go is a static language, so it's a type safe language. Some of the interesting things is that there are no kind of integer versions. So you can't assign an unsigned type, a value unsigned type to assigned type. Just by default, there is a conversion operator which lets you do that. Similarly, that obviously all array checks, all array subscripts and bounds checks when they need to be. So if we were doing I've got the S in here, but if we're doing something with SI for each iteration, at this point we actually fall off the end of the, if we're using C would fall off the end of that array. But bounds checking, it doesn't seem to be particularly controversial. It's just part of the safety guarantee. There are no dangling pointers. Importantly, so if you use a local a function local variable inside, so you can be very careful not to return the stress outside that frame. And go for your life. The compiler recognizes when you do that and will silently move that application onto P. Similarly, if it recognizes that it doesn't escape the frame, it will store the stack bar escape analysis. So, importantly, all the memory is zero if you don't initialize it. So in this case, Q is not initialized, so we put default value of 1. All the types have 0 value, which is value that if that memory was filled with zeros, that would represent. Obviously, here we haven't given it a type, but for integer types, the default type is. Importantly, there are no coercions from introduced booleans, unlike in C where if it is at 0, it's true. This is syntax error. You have to say if I greater than 1 is to have something that would have a Boolean expression there rather than saying I can be coerced to be something that is 0 and 0. Probably most people have heard about Go's concurrency support, Go routines. The bottom line is, and pretty much this is controversial, but multi-core is a reality. So the idea of a single core processor getting faster is not a reality. Multiprocessing through Python multiprocessing, what's the library that lets you sub-processing? Sorry.
Multiprocessing.
Yeah. I'm saying it's not a solution. For some things it is, but when you see the ease in which you can spin off a function as its own Go routine compared to the effort you have to do with multiprocessing, that's a much bigger story. Networking support is baked into the standard library. Most languages have a networking library. Ours is very tightly integrated with the runtime, so for writing the processes that doing all the pushing on data over the network, that the scheduler knows about that. Also the types that you interact with, network types, sockets, you interact very nicely with other types in the standard library rather than you have the capital file type dealing with file descriptors in C, but you have this socket thing dealing with sockets in C. So it's well integrated together. Data collection. Obviously to emulate, to remove bookkeeping errors using malloc free. But also when you have concurrent programs where one part of the program is generating data and giving it to another part, it's sometimes difficult to figure out the ownership of that data and when it's actually finished with. If you like Windows C++ programming, huge amounts of their API dedicated to who's allocated this, who's allocated should deallocate this. This is just completely another thing you can go. When everyone's finished with that value that falls out of scope, performance is good, getting better. The plans foot in the next 12 months for concurrent compacting collector. I find reading bug reports and views list, there are really two reactions to Go's garbage collector. Most people have no problems with it whatsoever. Other people, and all the remaining ones, they are people who want guarantees which we can't do. Like they want to do gap programming, they want hard real-time guarantees. I don't think Go can do that. I think it really wants to read allocator, manage their own memory. All the people that are just allocating too much, they are actually, if it's not garbage collection, cleaning up of their unused memory is not the problem, it's the fact that they're using so much memory in the first place, creating many buffers and then coming away. Speed, obviously, it's fast compilation. Speed is talked about a lot. It's a lot of press. But more importantly, these two quotes from Robert as well are talking about this idea that if there's a continuum of programming languages, that Ruby and Python, the dynamic language is down in kind of fast productive end. C++ is towards the but obviously fast, slow compile, slow work with fussy. And both, I mean, Rob is a big champion of this idea that this doesn't actually need to be. There isn't actually a choice between them. And Go very much as an attempt to demonstrate that you can be fast in all these dimensions at the same time. And obviously, we have, and this is mainly around thinking about when you're working in a large project environment, not just when you were two or three of your team working together, but when you're using code from at Google scale, where I think from my own experience in other jobs where I've worked, where a common library that we all bought about had 2 warnings that came up every time we touched it. And you just had to live with that because getting it changed is just, they're like, it's a warning, don't worry about it. So Go just takes the view that there are no warnings, only errors. So it's kind of starts. Unused imports this comes directly from, if you use languages with header includes, then pretty much they all end up including the world by these headers, and that has a huge impact on the compilation time. So we say if you're not using that import, it's an error to include it. So just always depend on any of the things that you need. And obviously Go format, the single way to format code, which is pretty much silenced all the arguments about ways to format code. Really, deal with the arguments that come up. I want to use space, or I want to use tags. It's just comes up very infrequent. It's just not a thing. So, quick go to some of the things in the language which make them similar, maybe different. Constants. Constants are quite interesting that there are different kinds of constants. So, string constant, Boolean constant, integer constant. These ideal constants. So this is actually 1/3. It's not the IEEE representation of 1/3. The real constant is 1 divided by 3. We store the divided and the big one. Yes. And so when you take this constant and you multiply it by 3, you get exactly. Now it's like if you're formatting library that's got a rounding up going, yeah, it's close to 1. Use exactly 1. How important this is, I think it's quite beautiful. How important this is really depends on your application. This is an example from Rob Pike's original talk where this enormous number could not fit into way beyond the precision of IEEE floating point, but you can still create the precise recipient of it. And it's done mainly compilation. Compilation is this compiles this high precision representation of full numbers. Usual types, there's nothing really interesting here other than these guys here. Byte is an alias obviously for an unsigned integer. So if you're using Java, you'll appreciate that because you actually have a real byte type and a real unsigned integer A type. Root is similar to Java's chart, except that it isn't defined as a UN16. It is an alias for one of these types, you just don't tell you which one it is. So if you're dealing with rooms, you don't have that problem of student surrogate pairs. They won't fit into a UN16. I think at the moment room is UN32.
It's in 32.
But it could change, and that's totally fine.
No, I don't think it will change.
It would, they'd have to add a lot more strange characters to the Unicode. You could set to yourself that space, but that's what we said about UN16s. All the rest of them are fairly variables. I've talked before about the default initialization. The short variable declaration is both a declaration and initialization, and is very, very powerful when you can say it's used all over the place. This would be considered to be a very verbose way of saying this. This is much easier, and it leads to things like os.open returns os.file and an arrow type. But we didn't have to know those types, we didn't have to declare them, we didn't have to say var f start OS file, error, and then assign them. Just all of that can be compacted down into this short variable declaration.
Is it there to reassign using that assignment later?
It is. So if you want to make yes, if you that is one of the disadvantages that, as Rob quite pointed out earlier on this year in Gopher Common, we do actually have more ways of initializing things than we need. It is a little bit. The rule is there has to be at least one new variable every time you use that. So if error was already declared, we're declaring F, that would be fine. It is very powerful because when you use this, not only do you not have to, you just don't need to know the type of F. You just get it through time threads. The last one probably everyone knows about the visibility rules to Go. There really are two. There's public, it starts with a capital letter, and exported and not exported. This is a package level. In terms of there's certainly nothing as complicated as C++ is for creating variables and things like that. It's almost the level of this is declared in the header file and this is not declared in the header file. So think about it that way. And this is all on the package banner. I'll talk about packages. So you really only have two other levels of visibility: exported and non-exported. And that applies to constants, variables, types, functions, anything. They're all the same. It's this tiny slide, which I didn't want to put in. All the expression syntax exactly like other CD. The only reason for mentioning it is that statements are not expressions. So you can't assign y to the value of x plus plus. That x plus plus is a statement, not an expression. That one doesn't seem to be as similarly, you can't do that trick of the kind of pointer and then check if that's zero. Mainly because of the way that there are no user coercions. So,
so the reason why you can't use these kinds of statements as expressions. So I can see in that first example, you could have y plus x plus plus, and say x was 1 before the expression been. Can anyone tell me what y would be? Y would be 1. Yeah, y would be 1 because the expression x plus plus value x is the value of x was before the increment. But there's also plus plus x, which will tell you, which will give you the value after. And so that's the kind of stuff that leads to a lot of bugs. In the second instance, there are many cases where you want to have an if statement where you're saying if x equals 1, you leave one of the equals out. And then you do an assignment, and then because the integer can be coerced to a boolean, it is always true. And so then you've got another bug. Both the legal C and both the silent can accept it.
The overriding argument is by making the language simple, by taking away these Q tricks, it definitely makes it more neat and more reliable. Arrays are, as working in most languages, what you think of them. They tend not to be that common in Go, mainly because two arrays. So this is obviously buff is an array of 100 bytes, and buff2 is an array of 20 bytes. However, in Go, each of these array declarations are different types. So you cannot assign the contents to 20 bytes of buff2. This guy compiles both each of their different types, which means that arrays aren't particularly useful, and that's fine because we have slices which are far more useful. Slices are not dynamically typed; they are dynamically sized to the vector. So both buff and buff2 are slice of bytes. Buff, we're going to make a new slice of bytes, 20 bytes, in there, and we assign buff to buff2. So this is creating a backing array effectively of 20 bytes, and buff has a reference to that backing array. And this one, they both have a reference to that backing array. This is really powerful when you read into a big buffer and you want to slice it up and work with a little bit of it. That's where slices become. And of course, you can slice an array into a slice. So B in that case becomes holds a reference to the first 10 bytes of this 100 byte array. I'm being very careful not to use the word reference too many times because it's unfortunately confusing connotations, and we just try not to say it because people always want to talk about pass by reference. Which is wrong. Maps, as you probably mentioned them, you can either make an empty one or you can come declare one in line. So key value is just a map of strings to numbers, which are populations. Adding to maps works as you would expect. Deleting from a map works the same way with this delete function. And an interesting property is that you both, if you ask for a key at the value map that is not present, so there's no key in there. There is because this is an integer type. What value you use that says you have an answer. In this one-arg form, we just assign it the 0 value, which is the closest we can do. In the 2-arg form, this will actually will return true if that key exists, or false if it doesn't. So you can essentially you can say, give me the value, and also check, is this value actually valid? Like, what's that actually a valid key?
You might actually set population at 0. You have no way of giving it 0. That's what's wrong.
That's exactly right. And think of Java as a string. Java string can be a string or it can be an element. That's just crazy. So we don't have that. If this was a map of strings to strings instead of population or some other thing, that would be the empty string. Right? And you need some way of determining the empty string or actually a value set in there which was empty. So that's what the 2-arg form is used for. Structs, pretty much you know them. C, C++, or all those languages. There's no analog for C's union. It really doesn't come up very much unless you're facing with really low stuff like Jupyter's calls, because it's fundamentally unsafe. So, 0 value of struct is the 0 value of all its component members. There are no constructors and destructors. You can either define them. So if you use the 0 value, if that's useful for you, or if not, you can use this thing called literal initializer. We actually just spell out, I want new food, A is minus C is B is true, C has a value. And although, as I said, there are no constructors, it is quite common to have a kind of new function which returns you one of these new types. If you need it to be set up properly for you, or you want to have some default values. Pointers, as you know, love them. Here, Q is a string, P is a pointer to that string. Try and change that better or worse. And print out the result. Importantly, there is no pointer arithmetic. Even though y is pointed to the integer x, you cannot do arithmetic operations on this. All you can do is say this. You can change what it points to. You can't. So if you have another like x2, say y is the address of x2, but you can't do operating. You don't do that kind of one pointer thing. Yes.
Well, assuming the underlying type is still checked, so you can't assign the thing that has a string pointer to a pointer to an integer.
That is correct. So in Go, there exists for every value type, there exists a pointer type that goes along with that. Almost cursively, there's a pointer type to that one. And this becomes important when we talk about methods, but indeed that. So this is an int. This is a pointer to an int. So again, you cannot get around the type system that way. There's no idea of like void style. Control flow, I'm trying to point out the things that are different or about Go. There is none of that single line if or else. Every if in the branch must be put in braces, even if it's one line. It's really readability to avoid those classical errors of add another case to the if statement which is not executed or always usually executed. Again, there are no need for parentheses here, and that's partially because most of the precedence difficulties of C have been resolved. So would anyone try and do that in C++? I'm doing a bit scared. So is the associativity of this higher than that? It just works in an interesting when you use Go format. It will group things which are associated together, which have precedence together. So we normally use pluses. The format actually draws that, puts them together, make it very obvious. The for syntax replaces while, do, until, those loops with just variants of syntax. Pretty straightforward. You can do a kind of while or until with a single clause there, so for until done, or just a for case without any conditions to loop forever. And maybe you have a breaking here on this condition, and then you're just going forever. For has a range version which works for array slices and maps. So for a range of number slices that you had previously, you get by default its index and the value of that, which is used very heavily. And also on channels with that. For maps, you get the key and the value of the map. The iteration order is undefined. So when you iterate using the syntax through a map, the order where you start and the order in which you go through those keys is undefined. So you need to do that in terms of you take the keys, sort them, and you insert a different order. Switches, I mainly mention this because I know Java's added this recently, but switch just works how you expect. Obviously under the hood it's just a big set of if-else's which the compiler's constructed for you, but it lets you do all those comparisons. So you can switch on a string. You can do that in Java for years. You can have multiple cases in the same line. I'm not showing the break go to continue fall through. Store time so it is the inverse of C. You get the non-energy. Yeah. So you don't have to say break. So you can see if you have a break and fall through the next case. You can go. The break is implicit. You always, once you match one of those conditions, you leave the switch unless you say fall through. I think I've written about 3 fall throughs in my life. It's very uncommon to write that. Functions, as we found out at GopherCon, the reason why it's a function is because Larry Page said to do it that way. Nothing particularly controversial about the max function. I've used heavily in Go is the multiple return values. They're not only useful in interesting cases like this, but forming part of the error handling strategy. The error handling strategy. You can also give names to not only your parameters of the function, but also to the return arguments. In this case, maybe it's useful. I try to think of like an example where you would need to do this, but arguably this would be a bit of a smell if you're returning all these strings to remember that particular position. Maybe you write a better function for that. Methods. You can place a method on any type that you declare that. So that's a very short way of saying you can place a method on based on anything that you wrote in your package. So what that does exclude is that you can't put a method on int. It is built-in type, but more importantly, you can declare it in your package. So you can't place a method on it, but you can do things like define your own type, which is Celsius is derived from the float 64, so it has all those properties. Whereas you define it your type, you can put that on if you like, and anywhere that you have a Celsius, you can now freeze it. Interfaces. Let's talk about interfaces. Go, we say it's an object-oriented language, but it does not have classing and subclassing. Instead of that, the way you would traditionally think of breaking down a problem, the example I try to use here is most times people demonstrate subclassing. So we can have rectangles, and rectangles and squares are actually a subclass of rectangles that their height and width is the same. And that's really a kind of if you're saying a parallelogram is a square because if the superclass is parallelogram, square or rectangle in the C++ or Java world are subclasses of parallelogram. In Go via interface, we say it has a, we can say square and rectangle implement the parallelogram interface because they have a height. So anything that declares the method set of the parallelogram interface, so anything that has a height and width, because it has those two, is a parallelogram. This silly example is not as powerful as the next one on the slide. So in this one, square and rectangle both have those two. So instances of square and instances of rectangle can be passed to this function. So typo, you can treat them as parallelograms. The key thing is that square and rectangle, there's nowhere on the declaration saying square implements parallelogram. You should be very used to it in Java. These two types implement the interface literally because they have these methods. And the poster child of this idea is the writer type, or the reader type from a standard library. Most of the most profound interfaces we have in Go really have one method: read, write, close, that kind of thing. And so anything that has a write method that conforms to this signature is a writer. Doesn't need to declare it's a writer. Doesn't need to the person the thing that calls it doesn't need to know anything more about it than it just has this method. So from the format package, we have fprintf, which is very similar to C's fprintf. It takes a writer and prints a formatted string. And so any of these things, like the buffer writer, the bytes buffer, which is an in-memory buffer, the network connection, file from disk, this thing called IO discard, which anything you write to it just throws away, they will implement the writer interface. That allows for great composition of like none of these had to descend from a standard writer or something like that. None of them had to come from some type of hierarchy. They just are writers because they have this particular method on them, so they can be writer. Packages define the boundary for compilation, so you're always compiling a package, and then the boundary for it, so you might import somebody else's package and to use their functionality. It's not the file, it's not the header. Packages are the unit of compilation you use. When you import a package, you import it by name, and then the name becomes the prefix that you always talk about. So it's forms printf. And if you had another printf that you imported by some other name, it would be you would distinguish it quite things. Importantly, circular dependencies are not allowed. This was taken simplification to make the compilation easier, mainly because it's probably a code style. If you have packages that depend in the circular map, maybe that's a code style. And so Go generally has a small number of quite large packages. So the network package, the HTTP package, rather than the HTTP client implementation package that you might find in Java. I don't know how you, don't really know what you break it down in C++. Concurrency, guarantees and channels. The guarantees are lightweight threads. Essentially, they have their own stack, they have their own local functions. They operate from your point of view as threads, maybe like coroutines if you're used to that idea. They're entirely handled within the process and mapped onto usually a smaller set of operating system threads. So you might have, it's not uncommon to have hundreds, if not thousands, of sort of process coroutines, all being managed by one or two operating system threads. The runtime language takes care of all that. So in this example, we go from the bottom to the top, open TCP port 2000. So this listener represents something accepting connections, and we pass that listener to the server function and use the Go keyword to run that as your own Go routine. From that point onwards, we can go off and do our other work. We start a listening on port 2000. The server just runs in this loop, accepts the connection. Every time this accept returns to the client, so it then runs a handle and runs it off its own Go routine. So the server is not blocked while handle does any work. Handle can work with that client connection and close it whatever it wants, and without having to do multi-processing or think about setting up unicorn in front of this. Now you just added a network server to your application without having to think about restructuring it to be a set of different binaries in the client and the server or anything like that. The ability just to run to say this computation, I don't need this straight away. Go and do it. And send the answers later. It's so powerful.
My observation is it plain empty that when you write instructions?
That's a good question. This is not an awesome example. When main exits, everything exits. It is. If I wasn't writing this kind of example of using Go routines, I wouldn't have put this code in. And that would have ensured that the server function never returned, so we wouldn't have to do that. But where this is very powerful, we have a package called HTTP XVAR, EXTVAR, which is a way of exporting kind of metrics out of your program via HTTP interface. So you just start with HTTP server on some random port, and that just manages itself inside your process space without you having to dedicate the thread or set up an event worker or do callbacks or any of that. Just runs off by itself, and then your main thread can do whatever the computation job is doing. The other part is if we have Go routines that are working autonomously, how do we communicate between them? So this little example, we make a channel of strings. By default, channels are unbuffered. And so that means that to send something on a channel, there has to be someone to receive from. There is no buffering part. We can have a buffer. In this example, we don't. And buffering works as you'd expect. You put something into it up until the buffer is full, and then you don't have that example. So we make a channel, and then we spawn off this Go routine running creating function, so it has a reference to that channel. This guy is going to try and, for each of these welcome to Go, for each of these words, it's going to try and send it down the channel. And then finally we close the channel. We'll talk about why we close that in a second. So that's started what we got to at this point, and then the other side of that channel is not ready to receive, so it essentially stops. At the same time, we've got ranging over the other side of the channel, so it's trying to pull the values off. The range operator is essentially a shorthand for it is saying receive from this channel and put a value into it, and do that until the channel is closed. So it's a way of tuning from that channel, and then it's going to bring that forward. So only when this coroutine comes to this point, it's like I'm ready to receive, can this one send? And so this is the point of coordination between those two coroutines. When this guy has finished, run out of words to use, it's going to close the channel. Close is a signal to others that there are no more values in this channel. Not only is it empty, but it's closed. Results, and so this program actually exit. So, so in the previous slide, we saw sending and receiving. Select is an ability to, it's a concept of waiting for a number of things to happen. And so in this send and timeout example, I have some data, wants to be sent to this channel, the caller can pass on that timeout duration, how long will it get to wait. I don't want to just, so in the previous example, this send would block until somebody else came along to read from it. And in some cases, maybe you don't want that. You want to try and send, perhaps if you can't send that data immediately, you have to write it to disk, or in use case. So select is a really good example of using select. So select will simply choose one of these cases. Either, in this case, we're trying to send data to the channel, so we're trying to put data on the channel. So if this was unbuffered, we need somebody else on the other end that would be ready to receive. If it was buffered, we need at least some capacity to put that in the buffer. The other case is time.after, and time.after is a utility function which returns a channel which will send a value after this timeout. So essentially, this function call will be true after this timeout, after timeout seconds or seconds. So in this way, either we can send data to the two channel, or we'll timeout. One of those cases will happen. That's the only way this function can fix it. We can also do it in a kind of non-blocking fashion, where we're receiving from some channel, we're coming, which has some work. Every time that's true, there's work to be done, appended to this slice of work. If this is not true, so if this case is not untrue, then we have a default problem, which is if there is no work immediately, then the default falls will come from the file. Mostly that will just have nothing, or its way of exiting out of the select. If there was no work, to do. So going back to the previous slide, this guy here is going to wait until, for as long as it takes for something to be sent down here or this close to happen. So using this default, when we come into this select, it basically atomically says, is there any work to do? You may have multiple, you can have as many select cases like shown two for fit on the slide. Or if none of these cases are true, then we'll do the default action. That's a way you can construct non-blocking behavior, non-blocking sends and receives.
So I'm just going to take this slide.
Yeah.
The case 2 data, that's non-blocking data. Is it going to...
This up here?
Yeah, there. It's sort of saying... So is this sort of spinning through there, just testing if there's anything to do, and testing time after until one of those things is true?
Yes, except for the spinning. There is no kind of... if you use two condition variables, you can see it's similar to that, but we set up condition on each of these things. And so then if 2 becomes ready, then we'll do that one. Right. Or if the timer 1 becomes ready, we'll take that action. I can explain a bit more about that afterwards, but I have to explain the implementation of how it works. But logically, this select clause, once you enter this, one of these has to be true. And that can take an amount of time, or you can use a construct like this to limit it. I haven't covered defer, reflection, CGO, error handling, or first-class functions, closures. It just has them. You can pass functions around functions, functions. That all just works in expect. Some stuff about an actual, so that's language. Some stuff about the implementations that we use day to day. The standard library is the usual stuff you expect from libc, then the library, all the usual string conversion types, that type of things. Excellent support for networking, excellent and very robust HTTP clients. So they have been through the ringer for several years. They have knocked most of the bugs out of those. TLS, so you can talk to HTTPS servers. You can be HTTP server yourself as well without having to put a patch in front of your application. Support for common encodings, JSON, those kind of things, just the niceties you expect. Tar, compression, hashes, that kind of stuff. Mainly the bar when the set of packages for Go was set was really what are the things that we need to build Go itself, to write the tools that come with Go distribution. And that mainly defines the shape of the standard library. One of the things I'm very proud of is the cross-platform support of Go. Although most people that I know use Macs or Linux, we have an enormous Windows community. Mainly not English speaking.
Mostly in China.
Yeah. And the Windows port was done completely, spearheaded by a guy called Alex Brandon, who lives, I think he lives in Melbourne. Did all that work and maintains it. That came completely out of the community. As I said, we support all the variants of BSD, Solaris, Google's native client, which actually powers the Go Playground, which is the kind of testing sandbox you can use to run the Go programs in. And a guy called David Crawshaw, this site is working on bringing Go to Android for some class of Android applications. To talk to the whole Android sphere of all the things that are in the Play Store and all those APIs is outside the line. But definitely having Go programs which can be installed in some form as Android applications is what one is working towards. And one thing I'm really proud of is the cross-platform is designed as the superset platforms, not the subset. So you have a single function which you didn't have in Java. It's so it means that we have really everything that you use in the standard library works on Windows, not on Ruby. I know them really simple that was terrible. And this is a huge thing for people who are writing applications in Go. Especially that there are several examples on the different presentation I can give where companies have started to use Go for writing the CLI tool for giving to their customers. Just one binary. They only need to make sure their version of Python is installed properly, their version of Ruby is installed properly. They don't need to bundle a version of Python with their application installer. And it just works out on a cross-platform. Cross-architecture, of course, support the usual suspects. Support RPC, although probably a bit rarefied, is in the works. That's one of two parts. The second part is GCCO, which is the front end of GCC, which is less popular, but no less a implementation of Go. We have two production implementations to keep us honest. There's a guy called Andrew Wilkins in Perth, and he's working on LLVM, which is the front end of LLVM. Elliot Stone, who is in the UK, is writing a Go to HAX, is the language compiler So there are a bunch of people who are writing compilers to the specification to keep precise. And I think of so when Ruby happened, Ruby guys produced this fantastic test suite of things that said if you can pass through this UI with the implementation, then from that point there were 4 or 5 competing implementations. Competition is nothing. So this is great to have multiple implementations. It's not like C Python. It's not defined by whatever C Python says that it is. It is defined by the specification and these implementations. The last bit is the tools. Using the other called the Go tool is the front end that drives your interactions with Go. It's a simple, straightforward build tool that drives building, installing, testing, getting remote packages. It works in the concept of a workspace. This is potentially one of the more controversial things about Go. Everyone likes to have their code in a different folder. Who puts their source code in work? What's their source in develop? What's their source in source? So you've got three competing arguments there already. And so to use the Go tool, you need to perform some very minor conventions about how you're going to lay out the source. And then you can go path workspace. Supports initial compilation by the substances, so files that end underscore Windows, whether you compile Windows, files that end underscore ARM, when you compile ARM processors. We use this heavily inside the standard library for doing cross-platform stuff. It seems to be less common for packages that move up and become more application focused rather than systems focused. And has great support for cross-compilation from any platform you can build for any other platform. So on this machine here, I can make a 386 Windows build of that command. And there are even people who are running web services that say, give us your GitHub URL, tick the boxes for which binaries you want, and we'll make your releases for your program. You're using exactly this mechanism. So cross-compilation just works out of the box. More tools, we've got Godot, which obviously reads your source and gives you, should be clear there too, nice package documentation. So, Godot is both a web server where you can go to look at your source online. It's also a command line tool, so Godot can net the symbol you want, and you can get essentially an page style documentation of it. The linting tool, GoVet. Because the Go compiler doesn't those areas, those new warnings. There are things which are fall within those. So VET covers that. The format obviously formats your code. The testing framework which is built in. You also get a coverage report. Just use -cover if you want, and you have built-in race detector. Performance, depending on your requirements, good to excellent. It's excellent on ARM64, sorry, AMD64, and all the platforms have improved over the last 300 different releases. Strangely worded graph, but from Go 2.5 years ago to now, we've seen phenomenal improvements in pretty much all the benchmarks. We have the projects want to main style. There's also some good stuff, you can look on those later on. Questions? That's all about. Well, yes.
Question. It's not it's more about I think there are 2 projects that is Canonical is doing a lot of work with its open stack. And also it's open OS project that is related to Docker for getting these isolated installations where you can deploy and start things.
What is the relationship between these two projects? Is like it's canonical between Canonical Studio and Docker?
Yeah, like the open OS, and I think Canonical is more focused on deploying these kind of things using Ubuntu as the system.
Okay. Yeah, the orchestration space in general is confusing and crowded at the same time. So Canonical's tool Juju is an orchestration tool which we use to deploy OpenStack. Docker, if you can say, is a competitor to OpenStack. It's a certainly different way of thinking about deploying applications. You declare almost in a makefile style. Install a set of packages and then run this command. And each step you basically snapshot in right. So a single file produces a set of changes which defines exactly what your application is. They're definitely in some ways competitors. Everyone's a competitor in that orchestration space. They're also solving the problem from different directions. Our ideas of Juju always work with multiple machines and certain services connected together. Docker is more focused on I want a way of deploying my application. It basically works on my machine. How can I get it into production when my machine's a Mac, or my machine's running Fedora, and they're running CentOS out there, or they're running. So Docker is a way of kind of isolating your application, or basically defining your application from thing that's hosting it. Program is
I'm just so interested, sort of following on from what I was talking about before about deeply interested in language adoption. And a fascinating talk with a friend of mine who's a hardcore C programmer who sees all the things that I see as good features that prevent you from writing bugs as problems in Go, because you can't leave variables undefined. How are you supposed to pick up if you use a variable wrongly using the algorithm if it defines them for you? Things like that. So I'm interested in what the sort of, is there kind of a metric or take up for the language?
I'm going to leave that question to Andrew.
Yeah,
that is the.
I just want to get an idea. When do people have to leave? Yeah. Because this 7:30 what time is it now? 6:30. Who has to leave in the next half an hour? Anyone? Is everyone else here for the duration? You don't have anywhere to go?
7:30 is what it's not 6:30, so
Yeah.
probably.
All right. Well, rather than taking like more questions today, maybe we should both just take questions and because it's going to be quick break. Then.
Yeah, we'll have a break. Everyone needs to do things to do on break. Thank you.
At the moment, we give a new platform. And then we say, so we take all the exams on small pages. So we use that to building service. And then we adopt the different stuff. I usually use application server and things like that. Actually, I think I should combine the two. All of this. There's a service. Now, and it's already got a set up for programs running this process and server around.
So that's students. And that's actually close. It's a single part of it. Which you both parallels this probably say. Issues relevant for just buy Russian track. I don't think that's interesting. The second thing is routine is almost any kind of access like this. And so that give everything channels up the solution. That's all because of that, big difference between the process and the process stuff. But you can't, I understand that can't be a remote mailbox and other mailbox is transparency.
So definitely there's as I understand the idea, the machine and environment is much more for us and
Well, that's what
sub-products can be changed.
Because the end is all it's going to take a bit of work. Various ways of being honest.
You will see that if you do the
you can just use it like a server, which is generally generating. So effectively, really easy. It's a declarative on the side. So the biggest thing and then so it builds a graph all of these and the relations function at one all the relationships this is what I should do now make functional self-functions machine functions. So when you're writing the language, you're not writing it as like it's flying you are because if you try and do that 3 times in a row, some people won't be sick. It's called function through this tries all the just says, oh, you're doing something else. Don't write it. Chef teams that chef come along and really make up for actually the guys that really chef and they just become frustrated like there's a little bit so that's you have this order too much. It doesn't necessarily matter if it's well that's actually fills a few other questions. So they didn't say but there was some you can set dependencies for explicit already when it so you put the slides, your passes, the server process instead of stacking it actually just send it off use the channel and then you start to work on some
One of the things that's usually done is the last time I tried was it's basically abstracting out the basis of so for instance
is it what I'm not sure. Okay.
we're going to send this message to send register to read You don't have to worry about it.
Go using their writing along the components you need to so that's what you do any use just to write so
Sounds like an answer. Let's go and try and solve the problem in single steps rather than become very, very much the problem.
have their big distribution jobs basically what it's that takes care of the big jobs. So we get from most of the jobs.
That's what I see in the program is
Toggles the difference of number ones and turkey. Click on it, just say you proceed to grab the image.
Yeah, it's not. So you can very much like you have web processes which are things you never do, and they actually get you request. So you get certain types of applications and you have very different work processes which are very efficient web processes. Web ones are started and killed on basically as requesting in that the work process is very much that idea to a real work process. Not mainly via this change there. You might be able to put on the shoes and making the text yeah, it's also go very much.
I have one job to do.
There's two bits. One, doing the level regulation is still it's not regular the main content is the best person solve it.
Yeah, it's like, we have to.
We don't have to closer to the the approaches that I have right now. That was solid citizens and mainly the most of the processes So really the native word size that you is doing 16 that's going to be 4, so it's just not moving around. Things like that. So you do want to keep them exciting. Mainly what I do exact types is I'll use two syscalls and things like that. Everything's a time for as a user, the channel, you need to catch you lowest because like you can bring it but I'm sure
what happens to the idea and do around. There are other systems always a good idea to take a big bite, but just get right before you go. So I have basically prepared a talk first, and then Dave delivered most of it, which is kind of fun, which is good. So instead of not saying anything, I thought maybe I'd just talk about something slightly different. So I have this talk here that is kind of an intro to Go, but it's more of a fast-paced kind of wild ride through the creation of a Go program that uses a lot of Go's language features and libraries and so on. So you can get an idea of how Go programs put together and what they kind of look like. Does that interest you guys? Otherwise I can talk about something. Alright, cool. So it's called Code that Goes with Grace. And the idea is it's supposed to show how starting with a simple Go program you can extend it to do more than it was originally designed for, and yet it still kind of retains its natural shape and sort of grows elegantly when asked to. So there are beginnings around. So obviously you've all heard of Go, my favorite language. I suppose I should say who I am as well. I am Andrew Durand, I work at Google in Sydney. I'm part of the Go team itself. My responsibilities are largely around managing the project. And so I do stuff ranging from working in standard libraries and tools, to giving talks like I am today, to writing blog posts and articles and various tutorials and all that kind of stuff. I also run the GoLang Twitter account, which I should either apologize for, or I don't know. Anyway. So Dave's already said a lot about what Go is. A few notable things: it's open source with a very liberal license. You can pretty much use it for anything. I'm not a lawyer. And it's the language, the runtime, a couple of compilers, and library tools, and docs. When I wrote this slide, we had 300 contributors. It's probably more like 600 now, nearly 600. So you can tell you exactly how many. Ooh. Any lines that start with a capital. And 562. Cool. So that's a lot of people, and most of them are not working. So Dave said a lot of what Go is, so I want to talk about what Go is about. So one of the things Go is about is composition. So Go is an object-oriented language, but it's not in the way you might traditionally think of object-oriented. For instance, Go has no classes. Instead, you just have types on which you declare methods. And so there's kind of this distinction between functionality and data. They're not intermingled like you have with classes. There's no subtype inheritance, which kind of forms the basis of a lot of traditional object-oriented systems. Instead, you support interfaces. They've kind of touched on this. Interfaces are satisfied implicitly. There's no structural typing. And so it means that you can have much more ad hoc, kind of serendipitous situations where one type of thing implements behavior, another piece of code expects that behavior, and you can just kind of naturally use them together without a great deal of refactoring and engineering work to make those bits fit. And so the result of this approach is that you usually end up with small, simple pieces that are connected by small, simple interfaces. The other thing that Go is about is concurrency. So Go provides some concurrency primitives, the lightweight threads, which are called Go routines, and the communication and synchronization mechanism called channels. And the end result of this model is that you can write concurrent code that's comprehensible. You don't have fallback hell that you get with sort of event-driven setups, and you don't have to manage thread pools and all that other kind of nonsense that you get in the sort of older thread-based world. Go is also about Gophers. And we have Gophers here. Hey! Yeah, you all get Gopher. You get a Gopher, you get a Gopher. The people who left early don't get Gophers. I wanted to kind of like tackle them. Yeah. So the core values of Go are composition, concurrency, and Gophers. So remember that as we talk. So perhaps absent from your talk, David, was the Hello World program. Register, but I can say, hello, beautiful Canberra. And I mean that in an unironic way. Not when people bag out Canberra, but I was driving through today and really impressed by how beautiful it is. Not architecturally, or in an urban planning sense. Simply that there's a lot of green and trees and birds, which I like a lot. So that's a Hello World program is pretty straightforward. I guess I'll just say what's here. We have a package statement, all the code forms of package. We have a package import statement, importing the string formatting package. And then we have a print line of that string. And this is a slightly more involved example. It's a Hello World net. Hello net server. I'm going to use later too, which I don't usually do. Can you actually see that on the screen? Yeah. Cool. All right. So here we have some more input statements. This time we're using log and net as well, some additional bits of the standard library. And what this does is it listens on localhost 44000 on TCP socket, just waits for an incoming connection. And when a connection comes in, it answers the connection and it prints the string hello down the connection and then disconnects. So the way we break it down, at the top of our main function, I'm going to use my function. At the top of our main function, we call the listen function, which passing the listen address and telling it it's TCP. That gives us two values: a net listener, which is an interface type we'll use in a moment, and which is an error value. And so in Go, the way you handle errors is you get these error values, traditionally called that's the variable name that I've chosen. And then you compare that to nil. Nil is the zero value of an error. And if the error is not nil, it means that an error occurred. There is some error value to deal with. And so the way I'm dealing with it is just saying log but fail, just like saying print that to the console and quit the program.
So fail calls to...
It does, yeah. Fail exits your process with a non-zero exit code, or exit code of 1. And so now that I have my net listener, it means I'm listening on my network socket, I can loop with a for loop, just an infinite loop. I'm calling the accept method of the listener. So that means this function called accept will block until a network connection comes in on the socket and I've got something to talk to. And then if I get an error here, that means that something's gone wrong, trying to accept the connection in the socket, maybe So it's been shut down, something like that, I don't know. But again, I'm just handling that with a done fail, fail. And then I'll call fPrintLine to print the string hello to the connection C, and then close the connection. So if I hit run, nothing shows up here, it means it's actually running on my machine now. If I go into another window and use netcat just to connect to localhost 4000, produce telnet, same thing, and you'll see that every time I connect, I get the hello string. So that's pretty cute. That's my hello network. So there's something kind of cool here. We were using interfaces without even really realizing it. We were using fPrintLine to print to this network connection C. But the interesting thing is that the network package and the string formatting package do not know anything about each other. They have no reason to. Instead, they both know about this I/O writer interface. And as Dave said, the writer interface provides this write method that takes a buffer of bytes and returns the number of bytes that were written. So basically, it's the write end of any kind of pipe of data. And the network connection implements this interface among its method is write. And so therefore, the network connection is also an I/O writer. And so when I pass it into fPrintLine knows, I just treat this like a writer and it does the right thing. And so this is kind of like a microscopic view of what's actually a tremendously powerful concept of code. So let's extend the example a little bit further, and instead of having a hello server, we'll have an echo server. So what this server does is exactly the same as before, except when we connect to the server, it will repeat back anything we write to it. And so all of this is identical to the previous example. The only thing I've changed is instead of printing hello to the socket closing, I'm now calling this IO copy function, and I'm passing it in the connection and also the connection. And the way IO copy works, I guess it's on the next slide, is it takes a source IO reader and a destination IO writer. And these are the definitions of IO writer and IO reader. There's a write and read method, and our network connection satisfies both. And so what copy does is it reads data from the reader and then writes that data to the writer. It's just a convenient way of, so you can read from a network connection and write into a file. But what I'm doing here is I'm just reading from the connection and writing straight back. So if I go back to my example and hit run, how it works. Amazing. But can anybody spot a problem with this work? Sorry.
Any click?
Well, I just hit kill or control Z. There's enough.
Haven't closed.
I haven't closed the connection, which is fine, but the semantics of copy that it will exit once it gets a read or a write error. And that could be end of file, which is a benign error.
So if you close the connection on the client side, it says, oh, okay,
yeah,
I'm done.
And then IO copy will exit and we'll loop back. So there's something that's probably too obvious maybe, which is if I have a second client, it doesn't work. And that's because there's only one instance of IO copy running. If I hit Control C, that IO copy exits, we loop back around to the top of the accept loop, accept the connection, and then start handling it. Unfortunately, it's all been buffered and it works, but obviously that's no way to write a production service. Into Go routines. So Dave already explained what Go routine is. So we can just use one. If we add these 3 characters to the echo server, G open space, we launch each a new Go routine for each incoming connection, and each of those Go routines handles the echoing of data back to the client. When there's a read or a write error, the copy function returns, Go routine shuts down, any resources associated with that connection are released, and it's fine.
Can you fix that?
Sorry?
Can you do that? You just keep on accepting
Yeah.
threads forever.
Well, you can leave it running, but my point is that when the individual connection disconnects, when someone stops that IO copy will return and the Go routine will shut down.
Yeah, sure.
And so, you don't have to worry about freeing all the resources manually.
I meant like if you were worried about not having 10,000 connections at once, can you limit?
Yeah, so building in any kind of like rate limiting or stuff like that is something that you actually need to write. But we're getting close to that. We'll see. Oops. So yeah, so if you write an infinite loop that spawns, that allocates things before you need to build that stuff. But so now I can test this by connecting from 2 different ones. And it works, they both echo simultaneously. So we now have a concurrent echo server. Alright, so it's not a very interesting example. It's pretty basic, it's easy to understand. But in the rest of this talk, I want to write a simple program that implements chat roulette. Has anyone ever used chat roulette before? It's a text-only version of chat roulette. Yeah, well, don't. Maybe just stop now. But basically, the premise is it's a random conversation partner matching system. So one client connects, another client connects. Server matches them together so that anything that one user types appears on the other person's screen. So the actual basis of the chat program is going to be really similar to the echo program that we've already seen. In echo, we're copying from one connection back to itself. In the chat program, we're going to copy the data from one user's connection to the other connection and vice versa. So we're going to actually have 2 routines. One copying in one direction and the other copying in the other direction. So here's a diagram, which I will use my laser, which in our echo server, this is what it looks like. We have this main Go routine here with an accept loop that's kind of accepting these connections and creating Go routines that run IO copies. So here we have 2 clients, each is seeing their own stuff, copies just copying back to the connections. In the chat server, we're going to have the same accept loop with network connections, but this time instead, we spawn this match Go routine for each connection. And the matches are going to somehow decide which one of them becomes the owner of this conversation. And in this case, it's the one that got the red connection that wins. And so the blue connection gets passed into this match function, it now owns both of them. It's going to call the chat function, and the chat function is going to launch 2 Go routines that do IO copies in each direction. So that's the basic structure. But the crux of it is, how does this part work? Right? And the answer to that is channels. So Dave mentioned how channels work, so I won't go through the explanation for it here. But basically, the way we're going to fit this new model to our echo program is to replace the IO copy in our accept loop with a call to this new match function. And so the match function is the most sort of subtle part of this whole program. And so what it does is it takes a connection and it simultaneously tries to either hand its connection to another match function or receive a connection from another match. And so one of those 2 things must happen for each matchup. And the way it works is we create this partner channel, which is a global variable, which is a channel of read-write closes. So that's an interface that is actually a subset of the network connection. And because we only actually care about reading and writing and closing, it's nice to narrowly specify that that's what we're actually using. And then we print a string to the connection saying we're waiting for a partner. So the first thing somebody sees when they connect is a little prompt saying we're just waiting for a partner. And then we enter this select block. You did talk about select, right? Yeah. So select is like a switch, but instead of switching on values, it switches on channel operations. And so each case is, I have 2 cases here, one of which is sending my matches channel to the partner channel. Sorry, I'm sending my connection to the partner channel. And the other case is receiving a connection from the father channel, and I'm storing that connection in a new variable P. So in the first case, if I successfully send my connection to another matcher, and note that this won't succeed until there is a receiving connection. I can't just send it off into the ether. It has to be received by another match function. If I succeed in sending, my job is done. This match function exits the select, exits the function, the coroutine shuts down. It's now somebody else's problem to deal with this connection. If I receive, in the other match function, I would receive the connection from partner, store it in P, and then call this chat function passing in partner and, the received connection and my original connection. So I'll just bring this back up just to, so this decision to pass this here is this match function sending its connection through the partner channel. The partner channel kind of exists theoretically somehow off to the side, but that's how this decision is moving. And so this chat function itself is actually pretty straightforward. This is the chat function. It takes A and B, which are each rewrite clauses, and it prints the string found one, say hi to both. So previously they were sitting there waiting with this string on the screen. Now they're going to see found one, say hi, and immediately we start two IO copies. We have a new Go routine running, copying from B to A, and then in the current Go routine, copying from A to B. So we've set up a bidirectional communications channel between these two network connections. All right, so let's take a look. If I connect here, so now I have one match function running in a Go routine, sitting there blocked in that select statement. It's sitting there waiting to either send its connection away or receive a connection. When I connect a second client, it enters its own match function, gets the same select statement, and one of the two cases has succeeded for each match function. And so now, and this guy doesn't care about talk, so just leaves. Meanwhile, so obviously there's a problem with our program. We couldn't ship this, or nobody would use it. And the problem is error handling. We didn't actually handle the errors at all. We just had these two IO functions running away in their own Go routines. When they shut down, nothing's coming out. So one party gets it talking away and not see the other one's going. So to clean up when the conversation is over, we'll just add some error handling. And so the first thing we'll do is, instead of using IO copy, we're going to create this function called CP, which just delegates IO copy. But notably, it takes the writer and the reader and an error channel, and this is actually a write-only channel error. That's what error is. It means I can only send error channel. And we call IO copy passing in the reader and the writer as usual. So this time we take the error value from IO copy. This value here is we're throwing away. It would be the number of bytes that were read from the reader. We don't care about that. We just care about the error value. So we seek the error value and send to this error channel. And so now in our chat function, we create an error channel. And then we launch our two Go routines copying from B to A and from A to B. And when either of those fails, it will send the error value to that channel. And so here we have a receive from the error channel. And that receive will block until one of the copy functions returns. And when one of the copy functions returns, it will either be a non-nil error if there was like a read error on the network or something like that, or it will be a nil value, meaning that one of the clients shut down their connection cleanly. In either case, if the error is not nil, we should log it to the console so we know what happened. And then we'll just call the close methods on both A and B. So we'll make sure that both sides of the network connection are shut down. And so with that error handling in place, you can see that as soon as I click out that top, as soon as I close the top connection, the bottom one exited as well. And so now we're actually handling errors correctly and shutting down both sides of the network. Cool. So that's all well and good, but who actually wants to chat over TCP connections? I'm used to you, we all do, but not over raw ones, I would wager. So we can modernize it by turning it into a web app, although this is getting a bit out of date now. It should probably be modernized by turning it into a mobile app. But I'm not going to do that now. But in the web, because everything in the web needs, everything in the world needs its web analog. So instead of using TCP sockets, we'll use web sockets. The distinction between a web socket and a socket is that a web socket runs over HTTP. So when your browser makes a WebSocket connection to a remote server, it first makes a normal HTTP connection, and then it sends a specially crafted request saying, please upgrade my connection to a WebSocket connection. And the server goes, all right, sounds fine for me. And then they can start talking bidirectionally, just like you would over a normal socket. There's a bit more to it than that, of course. It can't just be that simple, but that's the basic principle. And so we're going to use a WebSocket package from the Go.net subrepository. It's not part of the standard library, but it's part of some supplemental libraries that are part of the Go project. And also the built-in net HTTP package to serve the user interface, which is going to be HTML and JavaScript. So here's the start of my web server version of the program. I've thrown away all of the stuff I was doing with the net package, the listener and the exception loop and so on, and I've replaced that with some calls to the HTTP package. So I have here HTTP handle, and that's registering this function handler with the group, the web server, this slash. And so this is my HTTP handler here. This is a hello web server. And then I call listen and serve, passing in this listen address. And then that will actually listen on localhost port 4000 and start running the web server right there. And of course, I have to handle it there in case something went wrong. In the handler itself, I just write the string hello web, again using fprint, to the response writer. And so the response writer is an IO writer with some other methods on it as well, like being able to manipulate the response headers, for instance. And so if I hit run here, oh, I can't listen on the port because I'm still listening in this window. Try it again. So now I have a web server running on port 4000. If I visit that in the browser here, see hello web. And so the way the WebSocket package works is a bit like it sort of piggybacks on the HTTP package, but instead you declare a WebSocket handler instead of just a what am I saying? Declare a WebSocket handler instead of a normal HTTP handler. And so this is what my WebSocket handler looks like. It just takes a WebSocket connection, and then I'm using fscan to read a string from the WebSocket, logging what was received, and then printing the string back to, my mum's calling me, to print the string back to the WebSocket. And so that's the server side. Up here I have some JavaScript to make the WebSocket connection, and then log anything that I receive, and also print the string hello to the WebSocket. So if I run this WebSocket server now, and then I copy this code and bring up the JavaScript console, increase the font size, the stars align, still in connecting state. I need to do it separately. Okay. do it in two parts. So you see, I was able to send the string hello to the WebSocket server, get logged to the console, and I received the string how do you do from the WebSockets. So that's how WebSockets work. It just becomes a read writer, so you can just treat it like a WebSocket. I'm sure you can see where this is going. I'm going to take the program we had before and retrofit a HTTP interface to it. So I'll set up this root handler function at the web root. I'll set up a WebSocket handler at /socket. Set up a web server listing on localhost port 4000. And then the actual serving the HTML and JavaScript is going to be this really simple handle here, which uses the built-in HTML template package. This is a global variable declaration creating a variable called root template, which is just this HTML template that's kind of indicated here. I've cut a lot of it out because this is the Go talk and the JavaScript HTML talk. But the basic elements of it are you create this WebSocket connection, and the one piece of data that I'm sticking in my HTML template is here. It's the address of the WebSocket stuff. And so when I execute the template, writing it out to the user, I'm passing in the listen address of the server so that the WebSocket client has read it. But that's not too obtuse. It's also not very interesting or relevant, so don't worry if you don't understand what I'm saying. Okay. So I said that the WebSocket connection behaves just like a reader and a writer. That's true, except there's one kind of niggling detail about the web WebSocket works that means we can't just drop it straight in the place of the network connection. And that detail is that the WebSocket is only kept open as long as my handler function is on. Right? So when this WebSocket handler returns after printing how do you do, the WebSocket connection is closed on the server side, and the client's like, all right, fine. But if you recall, the way the chat program works is for each incoming connection, we launch a match function, and one of those match functions goes away and passes its data somewhere else. And so, if our handler was WebSocket handler and called that match function, as soon as the match function passed the connection to another match function, the handler is going to return, and then the connection will be closed. So the conversation is over before it's even started. Is that clear? It's not clear, but basically I need some way to keep my WebSocket handler running until both sides of the conversation are complete, regardless of which go routine that conversation is happening. So what I need to do is create a wrapper type for my WebSocket, and so the wrapper type is going to implement read, write, and close. And it's going to delegate any of the reads and writes straight through to the WebSocket. So if you read from my wrapper type, it just reads from the WebSocket. If you write to my wrapper type, it writes to the WebSocket. But if you call close, what it's going to do is somehow shut my handler function there. And so the way we're going to do that is we create this type called socket. It's a structure type with two fields. It has a WebSocket connection and a channel of Boolean values called done. And the read and write methods on my socket type, they simply call the read and write methods of the WebSocket connection. They delegate straight through to the WebSocket. My close, on the other hand, it sends a single value to the done channel and then returns the element saying, yes, we successfully closed. Meanwhile, my socket handler, when it gets its WebSocket connection, it creates a socket value, my socket value, and it sticks the WebSocket in there, and it creates a done channel in there. And then it launches that match function we saw earlier in a new Go routine, and waits for a message on done. So effectively what I've created here is a IO read-write closer that I can pass into match, the semantics of which sends me a message on done when whatever is using this course close. Right, so when the conversation is over, I get a message here, I can return to my socket handler and the WebSocket connection can be shut down. So there's a kind of annoying niggliness here, which is this. I'm sort of, you know, it's just boilerplate really. Like, it should be more natural to do that. Unfortunately, there are more natural ways of doing this. It's a technique called struct embedding, which allows you to have, say, a type A, which can be anything, that you can embed in struct B. So here I have a field called A. No, it's a field of type A, and it has no name. So you see on the previous slide, my struct fields had names in front of the type. Here I just put the type in itself. And what this means is it embeds A inside B. And it means that this method, hello, declared on A, is actually now a method on B as well. So this is commented out, this is not actually here. But the idea is that the compiler writes this method for you. It allows you to call A's hello through B. And so in a sense, B becomes a superset of A, right? And so if I call hello on B, it's invoking A's hello, right? So I can use that to great effect here, which is instead of having this messy couple of methods here, I can instead embed a read writer in socket. So now the socket type has read and write methods. And when I create the socket, I put the WebSocket connection in as the read and write. So when you call read and write on socket, you're calling read and write on that WebSocket connection. And the really nice thing about that is, now this is just an ambiguous kind of socket thing that doesn't care about WebSockets anymore. It just cares about read writers. So let's see a demo of that. So make sure I go to Windows. Okay, so now one of them is in that state waiting for a partner. Note that I haven't changed any other part of the program. Match and chat functions displayed. Yeah. And now I get localhost 1000 again. Second WebSocket's connected. I start typing. Oh. No, this is Web 2.0. Yes, it is. And when one of my connections, when I navigate away, the WebSocket connection is shut down. Both sides of the connection are closed. The other client sees the connection is closed and works quite nicely. So there's one. We're almost ready to launch. You said, what happens if you launch this product and the first person who connects gets the site and then there's nobody there to talk to? Well, it would be nice if we could actually synthesize a chat partner. So we can do that with Markov chains, which maybe some of you are familiar with. This is an extremely loose definition of Markov chains in this specific context. But essentially, you can take a string of tokens, in this case we're talking about words in text, English text or whatever text, break it up into words, and then you create these chains of tokens. For example, prefixes and then like an expected suffix. And in real Markov chains, you have some kind of probability associated with like the suffix that might follow I am. So in this case, we see with this source string, we generate this table of prefixes and suffixes. And you can see that there's only one situation that has a fork, that is I am would either be followed by A or it would be followed by not. The rest of them are all unique prefixes. And so generating sentences from the table, I can create sentences like this, and they can be infinitely long because I have a loop in the table. That's fine. But Markov chains are kind of fun. The more data you put into them, the sillier and more amazing they get, to a point. And then once you put too much text in them, it just becomes incomprehensible. But it's actually, there's a code walk on the Go website, go.codewalk Markov, which is an implementation of Markov chains, and it's actually quite nice. It has this is really small on my machine, but yeah, so you can go through the program and you click on each piece, and then each piece is described, and you can see that's implemented. So you should check that out if you're interested. Definitely a lot of fun to play with. But I'm going to just use that implementation here with a couple of small modifications. I've just modified it to be safe to be used in concurrent context. So I've just got a lock around that table of chains because I know that different users may be using either putting data into or reading data from one after chain tables. But the way it works is we have this chain type. It has a write method, so it actually implements write. Anything written to it gets broken up into words and then put into the table of chains. And then generate takes a number of words in, and will generate most words from table of chains and return that as a string. Okay, so to feed the chain of Markov tables, so the table of Markov chains, we're going to essentially siphon off any data that comes into the system. And so the way we're going to do that is by modifying the socket type that we have, the WebSocket and the type. And we're going to make it so that anytime we read from the WebSocket, we don't just provide that as a read on the socket type. We also write that read to the chain table. So we create this local variable chain with 2-word prefixes. And then in the socket type, we actually break it up. Instead of embedding a read writer, we're now embedding a reader and embedding a writer. And then in our socket handler, we do something kind of tricky. Before we set up the socket type value, we create an IO pipe. And so an IO pipe uses a reader and a writer. And anything that you write to the writer becomes a read on the reader. So if you write hello to the writer, the reader on the read end will see hello. So IO pipe is just a nice way of getting a reader when you have a writer, or vice versa. So I create a pipe, I launch a goroutine. So for each incoming engine, I now have another goroutine running up to the side. And this goroutine is using IO copy to read from the WebSocket connection. And it writes to this thing. It writes, everything you read from the WebSocket connection is written to this multi-writer. And a multi-writer is a writer implementation itself. And it's a writer implementation that takes any number of writers, and anything you write to the multi-writer gets written to the provided writers. So everything read from the WebSocket connection is simultaneously written to this W, which is the right end of this pipe, and also chain, which is the chain table. And so this will keep copying until it gets a read or write error or end of file from WebSocket. When IO returns, we will close the pipe's right end with the error value, and then that error value will be propagated to the read end of the pipe. And so if it's end of file, it will just close the read end with nil error as well. Otherwise, it will just propagate that error to the read end. And so now, when we create the socket, we give the read end of the pipe as the embedded reader, and we give the WebSocket as the embedded writer. So any writes will just go straight through the WebSocket. But it means any reads from our socket type are actually read through this multi-writer, through this pipe, eventually from the WebSocket. But on the way, our data gets pushed into this little chain table where we're generating conversational data we'll use in a moment. So we're now going to implement another read-write closer, but this time it's the bot that actually speaks to clients as they come in. And so we have this function bot that returns a read-write closer. Breaking the rules a little bit. You're supposed to stick it out. What? Oh my god. Sorry. I'll speed it up. Alright. This is the most fun part though. Okay. So the bot returns a rewrite closer. Anything that you and so I'm just going to jump straight here. It returns bot. It initializes the pipe and sticks that in the bot here. But the interesting part is that the bot, when you write to it, it launches a Go routine following the speak method, and then returns, yes, I wrote the full length of the buffer you gave me, and there were no errors. So it's just absorbing writes, and just doesn't care what data is. All it knows is that it's being spoken to. Meanwhile, the speak method, it sleeps for a second, generates a 10-word at most sentence, and then writes that to this outfield. The outfield is this IO writer, which is the pipe writer, which becomes a read on this bot. And so anything that someone is reading from the bot is actually getting writes from this speak method. And so anyone reading from a bot will just sit there blocked until such time as they say something to the bot, and then it waits a second and then says something back. Right. And so now we're actually going to get to modifying the original code that we had for the first time. Okay, so in our match function, we need to introduce our new synthetic chat partner only if there's been no response after 5 seconds. So we had our select, which we're doing the send of the channel partner, potential partner, or vice versa. And we had a third case, which is a receive from this time after. This is a helper function that returns a channel, and that channel will receive a message after the given duration. So it's a little helper function. We just say after 5 seconds, I'll get a receive. And so this case is fired if neither of these cases fire after 5 seconds. So it's saying don't let anybody wait more than 5 seconds for a conversation partner. So we call bot to create a synthetic chat client and start a conversation between the bot and the current user. The chat part of the program still remains untouched, the chat function itself. So I can demo this. This 4,000. Oh. So that worked. But I actually want to put some conversation in there before I start doing this. So I'll say, here's the current state at the end of what we expected before. Hey, how's it going? Pretty good. You. Fantastic. Great. Okay. All right. So that's our scintillating conversation. If I hit refresh, connection closes. And now I'm waiting for a chat button. Found one. Oh, and he's already started talking. Pretty good, you. What? Really smart. Anyway, so you can see that now we have our synthetic chat button. And now, in sort of typical Steve Jobs style, I must give you one more thing, which is TCP and HTTP at the same time. And so the way we'll do this is we have our main function with our HTTP stuff, but we have this line at the top, go netlisten. And netlisten is a function that is just our main function from before. It sets up, this time we're listening on port 4001 for TCP connections. And it's the same except loop that we had in the first iteration of this program. So if I run that version, and run my inverters, let's see lots of animations now. Alright. So now I can hit localhost 4000 there, and sorry, I need that. So I'll go to localhost 4001 here, localhost 4000 in the browser, and now we can chat to each other. Oh yeah. And then the cool thing is, you know, when I go back to the console, the bot still works. So that's also fine. So shut that down. All right, so basically what I was trying to show here is that, this is not this is an example program, but I actually started writing this program with the goal of experimenting with this sort of chat roulette concept. Basically, the first iteration of the program is the one that I wrote. And then I thought, wouldn't it be nice to add X? Wouldn't it be nice to do Y? And what I did there is exactly what happened. Like, I didn't go back and smooth out. I mean, I smoothed out a little bit just to take out a couple of little, make it easy to explain. But in general, this happens time and time again with Go programs, that as they grow over time, they just kind of grow naturally, and you don't really have to go back and do big mass refactorings and stuff like that. Maybe that's not true to other people, I don't know, but it is kind of has been in my experience. That's kind of what I'm trying to show. Cool. Yeah. So, thank you.
I was going to ask why in the initial main loop you just didn't do connection 1 equals accept, connection 2 equals accept, and then chat C1, C2. But at the end, when you're being able to take readers and writers from either, that's where it accepts.
Yeah. And it's, the thing I like about this talk is it illustrates some really profound subtleties to do with how you use interfaces. So we saw how all these unrelated pieces of code can implement the same interfaces and can be used together dynamically. And it also shows some subtleties about the concurrency model. A lot of people sort of think of in terms of one thread per request. You have a request coming in, and you launch a thread to service that request, and that thread services the request at the lifetime of the request. Whereas what we saw, at least in the first example of the TCP chat server, the initial Go routine that was handling the request, it died very quickly after accepting that request and handed it off to someone else to service that. And that is another pattern that you see time and time again in Go programs, which is resources being handed away to some other part of the process, and then whatever earlier part was dealing with it just going away. And both of those kind of ideas are really powerful, and so I'm glad that they're together into this. I don't know how much time we've got, really running on. I've answered any more questions.
Just a small one. Because you mentioned that for using the Markov chain, you were using the log. Is that something that you can fix using a channel, or not using the mutex or?
Yeah, so it's a pretty common question. So Go has channels, which are a great way to communicate between Go routines, as we saw. But it also has this package called sync in the standard library, a sense of synchronization. And it has things like mutexes and weight groups, and these kind of useful little utilities for writing concurrent software. And they're more traditional, kind of traditional approach. They're there for a reason. They're there because they're useful. And so if you have a shared data structure that you have many readers and few writers or whatever, often modeling that for mutex is the simplest, easiest way of doing that, and that's when you should use mutex. Channels allow you to express things that previously you would have had to use things like mutexes to model, but it lets you model them in a much more natural way. If you try and do this thought experiment, how would you do that chat partner handoff thing using locks? Unless you're quite experienced with writing concurrent software using locks, it's not a simple, it's never a simple thing, but it's not even tractable for someone who's not experienced. I guarantee if you try, you're going to get a bug straight away. So, yeah, in the case of that shared chain data structure, using a mutex was just the most natural way. And so, fortunately, Go allows you both approaches. The only downside of picking one or the other is that one, depending on the situation, one might be more or less verbose, or more or less error-prone. I'm also happy to answer questions way broader than what I just talked about, anything to do with Go. I can give you an idea of like the basic. Who here is in scientific computing? Look, only one of you now. I was going to say stuff about it, but now I'm talking. Cool.
I prefer like a graph book or just I don't know
One for each, so we can run this program and just do this program that takes the laptop.
Well, okay, so far we've had people who ask questions. So you give a question. You keep it going for a question.
What about the function I'm running?
So Go is not a functional language. And its type system makes it very difficult to write the generic map, say, or zip, or any of those kind of staples of functional programming. And that's because it's not pretending to be a functional programming. Like in a language like Ruby, you have all those primitives, but they're not actually operating over lazily evaluated data structures. They're actually operating over arrays and so on. And so you get the expressiveness of the functional programming language. You don't actually get the efficiency in Ruby, for instance. But because Go doesn't even pretend to be that, you just have to write the for loop. You just have to write the code that does what it's actually doing, rather than kind of abstracting that away. And so it's definitely more verbose at times. But I think in terms of code clarity, it's a lot easier to understand the performance characteristics of Go programs than, say, Haskell programs. So if you go into Go trying to treat it like a functional language, you can go in and have
the functions can be passed around with
Oh yeah.
I was going to add one thing that's happening more and more in future where you have to implement an authentication layer. And so rather than having like a type called the authenticator type that answers all the questions, we actually pass to things that need to be authenticated functions, like can read, can write. So that function is called by the thing that needs to do with the authentication passing the credential type thing. And
there's cool examples even in the standard library. Like you look at, say, strings package, which is just general like string manipulation kind of thing. You have, say, index func, which is a function that takes a string and a function. And the function that it takes a room, like a Unicode character, and returns a boolean. And so that function is like a test. Is this the character we're looking for? And then it returns the location of that character. And so you can see this implementation here. We actually create a function value on the fly, f, which just returns whether it's a Unicode character. And so we can see, in the case of the first string, I think it's that character. And in the case of the second string, it's not present, so we get negative. And of course, this could be a closure. I don't know what it's called, but if I take this out here, and put that outside, now our f function is actually closing over this value t. And if I change t in between calls, and I need to consult library no time to. So now I will search for something Roman. Well, Latin, that's what it's called. Yeah, Unicode. Now I was, oops, oh, no. Oh, it's that one, okay. Oh! I wrote this code so I can be curious at it. So first it's looking for a one character. And then if I change t to be Latin, we should get the location of h, which is 0. Yeah. Closures are actually really awesome. They almost weren't in language. Canton thought they were going to be too expensive to implement, and then another one of our programs for us implemented it while Canton was on holidays.
Do you have the used alcohol organisation?
No, Go doesn't do alcohol, and there are no plans to introduce. Mainly because I think the rationale is that it would introduce, it would force people to write in a particular style. And that's just the resistance. Yeah.
Google invented, or not invented, but just start using the MapReduce thing or functional things after they design language. Why they don't implement these kind of things in these new languages? It's because they are moving a lot of these MapReduce things into doing concurrency, or?
No, I think there's probably a misunderstanding of the distinction between, say, functional programming concepts of like MapReduce and what MapReduce is like in practicality. Like Google's MapReduce framework is a big C++ program, and you write C++ programs for it. You can also write Java programs for it and Go programs. But we actually have a language called SourceForge, which Rob Pike also designed, and that was specifically designed for logs processing. But, yeah. And SourceForge was written basically as a declarative kind of functional language with inputs and then processing directives and then outputs. And so that was kind of the solution to that problem. But like MapReduce is tremendously useful over large data sets, but programming in the small with like MapReduce features is not the same thing on abstractions. Sort of all the time.
But the notion is Google is using both, like for different kind of projects.
Well, we use MapReduce, which is a system, and then we just use whatever program we use to drive that. But like, when you do a MapReduce with Google, you write a program that implements a function called map, which takes an input and then you do stuff, and then you emit outputs. And similarly, when you write a reduce, you don't use like a reduce language feature. You write a function called reduce that has some inputs and some outputs. So it's really quite separate from functional programming.
This new testing project or something, you said there was something before about testing.
Yes.
So you can test something to support that language? Or?
Yes, it's in the tool chain of the language itself. In really short terms, a unit test would look something like this. So you would have a file in your package called something underscore test of Go, in this case string, and then you would have a function called, say, test index. It just invokes the function of the test, gets its output, compares it with the equals, not equals, and then uses this T object to log an error message to the testing framework. And so when I run go test on the current package, I'll use -b, so I see what's going on. It compiles my package with the test path included, and then runs any functions that begin with capital T test. And then you can see them in the test framework. And the nice thing about this is it's really, really minimal, but you get the full power of language at your disposal when you're writing the test. So if you know Go, you can immediately know how to write tests. And the standard library is very well tested. And because this is all right there, most Go code tends to be, at least have some tests.
Test files live in the same place as the rest.
Yeah.
That's important because I think there are two phases of compilation. You have like normal compiling. You can also have compiling tests with your code, so they have access to the same symbol. So that kind of information work around the public and private nature of symbols.
Yeah, so it means you can write tests for the internals of your package, because the tests also live inside the package.
Yeah.
So you don't have to explore like parts of your libraries, like testing styles and so on. And I actually have another talk, which is online. It's called Testing Techniques. Search for Go Testing Techniques, you'll probably find it. Where I show how I can introduce these little stubs internally inside my package and then override them during test to insert some like instrumentation. You know, in the case, in that particular example, I'm testing a program that depends on time. And so I actually stub out like time.sleep and some other stuff while testing.
Yeah, how expensive is like creating and destroying those workers?
So for a Go routine,
Yeah.
like a Go routine is at the moment it's about it's 4K again. Yeah, so it's like a 4 kilobyte allocation just because it's a stack, and then the stacks will grow depending on how much stack you need. But yeah, so there are Go programs that spawn hundreds of thousands or even millions of Go routines. It's just dependent on the amount of RAM you have available. The scheduler itself scales really well. We have probably the preeminent expert on multi-core programming hacking on Go just because it feels like it's about talk to me everybody I've got. It's pretty amazing. And yeah, his whole thing is making things scale really well.
And so, yeah, sorry, if I got it right from what you said, it's one routine is one thread. Is that not
No, so the way, so programmatically to you, a Go routine is a thread. But to the operating system, we actually multiplex many Go routines over a single operating system. And so in an ideal case, you would have roughly as many operating system threads as you have cores in your machine. And then the Go scheduler handles all the scheduling. Because the Go scheduler is much more aware of the behavior of those Go routines. And so it's going to do a much better job of co-locating related Go routines to the same threads.
Let me get the PHP thing where it's
Yeah.
blatantly spawning thousands of threads open. God, we can hit.
If you've got value take routines in that this sort of back and forth, well, they get interrupted.
They do get preempted now.
Yeah.
You can craft Go routines that can't get preempted,
Right.
I believe. I think just an infinite for loop will not be preempted.
Right.
So if you just write garbage code, you can lock up the scheduler.
Just kind of just lifting it up a level from the operating system. You're saying it's really.
Yeah, or down a level, depending on where. Yeah.
Do you find that you have problems with the core stacks? Like I know in Node, we've always got problems with the core stacks. Really small. If you're firing off lots of routines, is this like can you?
No, I mean stack size in Go is I think it's limited to 10,000 40 now. It used to be limited purely on the amount of RAM you have. It would just keep going. Actually, no, it's not limited, is it?
There is a limit. It's ridiculous. So
It's a big anyway.
Oh no, yeah, it's in.
We're not getting like an
so the stack starts on a page. You can grow. It used to grow and shrink the page design. Now it's more sensible that if actually the realistic work facility needs to be as large a specific pattern. That does mean that instead of like a static thread for an application, process threads of TDP that we or easily go badly, you can theoretically use your entire work this way. So if you write a person code, that's one of the things people can do writing triggers the print themselves, which is constants again. Previously to that, in about 4 or 5 seconds, your machine would start to stop really hard, and you couldn't stop it by then you have to kind of cycle it.
But you're able to see like, hey, like this is where this routine got into.
Oh, absolutely.
You're able to see back to the
That's good. What do you use from run test process and you control?
Yeah, so if I write a really simple program.
It's like using a document.
Yeah, okay.
Just to show
Actually, I've got this present tool running, right?
Yeah, anyone coming from any sort of async type backgrounds can be concerned about this.
Yeah, so my presentation software is running in this other window somewhere. Yeah. right? So there's a few errors in there. But if I do kill, is it up? If I do user one, quit. If I send a quit signal to that process, there is one which actually just prints this. Anyway, didn't want to kill it. There you go. Now we can actually see all of the stacks in my running program. So I send C quit. I can see go routine 0. Yeah, that's running the timers, I think. Go routine 1 is in network file wait, so that's the network file. Yes. And then the other ones, where's some of my code? So this is my code. Here, this is running the WebSocket connection that was doing the execution programs as well. Anyway, and you can see where they're blocked as well. So you can see this one's been blocked in Select for 33 minutes.
So that finalizes that they require between these average collection.
That is correct. Finalizes not guaranteed.
Yeah, the same thing that Java guarantees. It's fine. Very open exit, no finalizes.
When you saw for each coroutine that you create, there was one that's created by
Yes,
that's
the
the
last one.
the code and the function.
So this came from the socket map, which is really, and it's actually possible to get this from a running program. Inside Google, we have some more fun toys that fit into our other tools, and you can like inspect the state of running processes and stuff. You know, that's gradually.
All that information is inside the code program in particular.
Yeah.
It's the easiest way to get at it.
And so could you reload modules on the fly? Like I know we do a fair bit of that in Node. Which is not.
Standard line.
That's
Yeah, they're just you just have to recompile things.
yeah. Alright, that's contained for that.
You should embrace microservices. I believe is the new
Yeah.
where all of your processes should be. Yeah, very small. So you just restart any of them if you need to.
Yeah, you know, like you could always walk it out and say you can restart it.
Yeah, I had a very strange argument in a situation very much like this. The guy in the Netherlands was trying to tell me that we had to have this hot code reloading support in Go. Otherwise, there was just no way we could be serious about anything. And I was just
He's got once in Node and he's like, yes.
No, he was saying he did a lot in Java and it would be integral stuff. And I just thought, I'm just so glad I don't work in that environment. And it's really scary to me. I don't trust my own processes when they run correctly, let alone replace parts of them while they're running. Yeah, what could go wrong? The worst thing that could happen.
So the presentation software that was showing us, that was a Go program.
Yeah, there's a Go program with the HTML front end.
That's yours.
Yeah, it's just,
Yeah.
well, that's something that I wrote for Rock Pine to give a talk with Google I/O because he wanted to give a talk with about concurrency with Go programs executing in the slides and being able to show the concurrency behavior which involves time. And so I wrote a thing that used WebSockets to stream the output to the browser. And there's actually a talk about the talk software, validated software, in that talks.go. We just kind of meta, but it's pretty interesting.
So the code you're typing in is being compiled, Go.
Yes, every time I hit run, it would actually compile the executable and execute it. So that gives you, and the same thing's happening here when I use this, except it's happening on a server in Google's Data Center. But that just gives you an idea of, you know, how fast the Go compiler actually is. That's definitely dominated by the round-trip latency of going to California or wherever, and through my phone as well.
Do you think there was a specific use case in mind about it? Like, is there a particular problem with it?
Definitely. Go was created to solve the kinds of problems that we have at Google. The way Google is kind of arranged internally is just a huge number of servers that talk about servers. And they just communicate via an RPC mechanism using protocol buffers as the encoding thing. And that's kind of a joke that like the Google programmer is just someone who takes data from one protocol, puts it into another protocol and sends it somewhere else. And that is actually not really that far from the truth. It's kind of funny. But yeah, so we have so many of these like highly concurrent servers that need to be quite efficient. And so Go was designed to kind of make it easy to write those kinds of programs.
So doing it sort of like this market would be network programming or
Well, when it was launched, it was called systems programming. Then everyone seemed to think that meant operating systems and compilers. But that's not really what we thought systems programming was. But that's just not a very useful label. Network servers would be what it was designed for. But it's turned out that it's actually really great for a lot of things. The thing that surprised us is that a lot of people who were web development or really got into Go. My background is actually predominantly web development. And so for me, I found Go very attractive. And I'm definitely the only one on my team that kind of background is pretty interesting position for me. But yeah, we've since found that it's been useful for a huge variety of things. It wasn't designed to be a special case language, it's still a general purpose language. But definitely if you look at the libraries and everything that gives you everything you need to build those kind of network servers out.
yeah.
Do you have another question?
Probably the biggest place we use it is tools. It's so easy to run to using it. It is, yeah, I think it's we've got people in our company that are Windows, the people on DX, the people on Macs, and currently we've got everything in Ruby.
There's a lot of command.
Yeah, they all come up on
They notice it's supposed to written itself. No one expects.
and they're all written in Ruby, and I spend so much time with something like, oh, I can't get Ruby 1.9 running on
The lab sheet guys, yes,
and then they've got to run bundle, and they don't think Gearing won't compile on a Mac anymore. Yeah, screw that. That's what
Whereas I have this tool called WinStrap, which every now and then I need to do something on a Windows machine with Go, because I have to support out Go Windows users. It's one of those things fully releases. And so I have this tool called WinStrap, which is basically a Go program that downloads Chrome and Mercurial and a C compiler and our other tools, and then it checks out the Go installation and compiles and builds it, whatever. And the cute thing is, all I need to do is, in my WinStrap directory, set goos equals Windows, and then go build, and then it creates an exe file for me, which I can then send through my desktop to my VM and run it, and then does all the stuff. And this is all I had to do to get this functionality was just run the Go toolchain build script with that environment variable set, and then it just creates the libraries and binaries.
Is that public on code.google, or is that?
Yeah, that's public. It's cool. It's actually really useful. I mean, it's a big kludge. It's kind of bash script level kind of program. Oh yeah, so if you go to the WinStrap homepage, you can actually just grab the latest exe file and trust me, which I guess you should. Yeah. Well, do remember that you're using a file that was right back in the so.
But the list of things, it's not coming from a file, it's embedded in the code, but it's
It's in the code,
yeah.
Oh no, the executables are still wherever they're hosted. Like it does HTTP requests.
That's what I mean. So if you want to use it for your own environment.
Oh yeah, you would, But presumably this is just stuff that anyone, any sane person wants. Yeah.
The goal is not to make it's the fact that is there any make on Windows? Oh, you can see yes, it does exactly one thing and gets it. I think this producing tool is something that I don't think anyone saw it. So I it's very huge.
Well, like the Heroku people had problems with their command line client taking seconds to start, like to get the help message would take seconds, which is totally unacceptable. Like I don't know about you guys, but whenever I wait more than like half a second for anything, I tab into something else. The next thing you know, I've been reading Wikipedia for half an hour. And, you know,
The cloud foundry guys are exactly the problem. Their CF client is written in Ruby, and almost all their support cases are not about using cloud foundry, it's about running client.
Someone's writing Rail, which means they've got Ruby 1.8.6. So we have looking to write the stuff for 1.8.
it's interesting because none of this stuff is really new. They're all old ideas. Like statically we compile binaries with what old binaries.
Yeah,
Like liquid, that's all, everything's like that.
Yeah, but I mean, you know, that's just what software was.
Yeah.
And now it's like, oh, this is actually a good idea.
So I come from a VM where you do containers and units so when you're talking about the network services, this way you have to think about how you can scale. Is there infrastructure or patterns around how you want to do that, or
That's it. How would you, so if you had like applications doing some HTTP serving, how would you make that run on your machine? That's what you're trying to do.
right?
You say you bake it into an AMI and put it behind the cloud front room or something like that.
Yeah.
They're both, again, not using Go lets you write that hardware solution.
Right, so it's not sort of, there's not a pattern there, it's just like this will just give you this view and you sort of have whatever you
Exactly.
infrastructure.
But the interesting thing is that a lot of these infrastructure pieces fit into this picture and now also being encrypted.
Right.
I mean, like Docker is written.
Yeah.
A lot of these cluster management tools now being.
All actually comes.
Yeah, yeah.
It's all Go.
Yeah, like Core OS using Go, you know, all this kind of cloud systems infrastructure stuff. And I think the main reason they're doing it is because Go puts you really close to the system, so you can actually work with the network and the file system and everything really easily. And also with concurrency stuff. And that together is just.
The Go seems to do pretty well in the shootouts, like the framework shootouts.
Yeah.
Performance-wise,
The web framework one's definitely. Yeah.
because it's maybe level the efficiency.
Well, actually, the reason why Go does well in the web framework benchmarks is because Brad Fitzpatrick decided to make it his personal mission to make it win the web framework benchmark, which is a testament to Go's applicability in the facilities line,
Right.
as well as Brad's programming skills. But we all benefit from that. Yeah, it was like, why should we have to put Nginx in front of our web server? Like with Go, you just serve with Go.
Yeah.
Like, I think Nginx still has the lead on, say, serving static content from disk. Yeah, it's probably more finely tuned than Go. But the Go implementation of that is like 50 lines.
Yeah.
And I wrote it. And I'm not word Nginx, not by a long shot. But I didn't need to be. That's the that's the nice thing.
Project. Guys have one massive recap of everything that's in code.google.com.
Yes.
That's kind of encouraged.
Well, no, it's not everything's in one massive repo. We have several sub-repositories as well. The goal is, with project management, is you should maintain stable APIs when you publish libraries. And if you can break the APIs, put it in a different import file, so give it a different name. And that way, versioning doesn't have to be about versioning this particular import file. It's about changing the import file when you want to use the new version. Right? That's only if you're breaking things. You're going to break the APIs. But yeah, general project layout is just whatever makes sense. There's a good talk on it actually from this year. I think this video for you. It's not obvious. Just because the biggest struggle we've had internally is we're so used to the root way, one git repo per project, and you lay it out this particular way, and trying to break that habit, and then finding it around is. Well, so inside we have one source repository for everything. And so that actually solves a whole lot of problems and also causes a lot of tries. And I kind of find it really hard to break
other running and you've got to get your whole team to be able to do that. I've done change and done that.
I think it really depends. Whatever approach you take, it's mostly about the convention and discipline you create around it. There's no technological solution to this problem.
One very popular source you can go from students by example just talked about how they do it, like they're very polyglot company. I think at the end of the day they're essentially how to get something sub modules. Trying to remember the one that wasn't broken. Where
Peter Walker on David 12.